Earlier in the semester, we discussed how to determine the equilibrium points for stock flow systems. More recently, we have worked to describe what happens in systems when they are changing, that is, not in equilibrium. This includes our work on exponential and logistic models. In the remainder of Chapter 4, we will focus on understanding the relationship between these ideas. How do systems move toward and away from equilibria, and how are equilibria themselves changed by various factors in the system? To begin, in this video, we'll define the ideas of stable and unstable equilibrium points, and then apply these ideas to several examples. Let's start by clarifying the terms we're using. An equilibrium is stable if after any small disturbance from the equilibrium, the system tends to return to the equilibrium state. An equilibrium is unstable if after any small disturbance from the equilibrium, the system tends to move further away from the equilibrium state. A useful example is balancing an egg. If you lay an egg on its side, it will balance there. Moreover, even if it gets bumped, it will tend to settle back into the same position. This represents a stable equilibrium for the egg. But it is also possible to balance an egg on its end. However, in this position, any small disturbance of the egg causes it to fall over. This represents an unstable equilibrium for the egg. Let's start with one of our earlier attempts to model the Earth's temperature, the naked planet. At the top, you see the stock flow model. The stock is the temperature of the Earth's surface, and short-wave solar radiation is the input for this system. The outflow is due to long-wave thermal radiation. The inflow and outflow are marked with a plus and minus, respectively. As we discussed earlier, the amount of thermal radiation is dependent on the temperature of the Earth. The warmer the surface, the greater the thermal radiation. We represent this with a positive control arrow. Note that this creates a feedback loop with one negative sign. Using the rule of signs, this gives us stabilizing feedback. On the bottom, you see a graph of the inflow and outflow for this system. The inflow in blue is constant. Recall that Stephan's law predicts that the outflow is dependent on the temperature of the surface. This determines the green curve for outflow on the graph. We know that an equilibrium occurs when inflow equals outflow. We can see from the graph that this happens when T equals 255. Now let's think about the stability of this equilibrium. For any temperature below the equilibrium, the outflow will be lower than the inflow, causing the Earth to heat up, returning it to the equilibrium. On the other hand, if the temperature is above the equilibrium, then the outflow is greater than the inflow, causing the Earth to cool. Again, the tendency is to return to the equilibrium. In other words, T equals 255 is a stable equilibrium for this model. Putting this all together, we can see that this system has a single stabilizing feedback loop, and this results in a stable equilibrium. Here's another example from earlier in the semester. Consider an investment which grows 10% per year and from which you withdraw $1,000 per year. Here, the outflow is a constant $1,000 per year. The input, the interest earned, is directly proportional to the account balance. This creates an amplifying feedback loop in the stock flow model. The graph at the bottom plots the flow in relation to the stock level. From this graph, we can see that the equilibrium occurs when the stock level, or the account balance, is $10,000. If the account balance is below this equilibrium, then the withdrawals will be greater than the interest input. The account balance will drop further. On the other hand, if the account balance is above the equilibrium, then the interest will be greater than the withdrawals, and the account balance will grow. In either case, the tendency is to move farther away from the equilibrium, making it unstable. In the previous two examples, we saw that there is a close relationship between feedback loops and the stability of equilibrium points. Although this is true, more complicated feedback relationships make this less direct. Here is a population model to illustrate this. Here, the stock is the population, inflow results from births, and outflow results from deaths. Note that both births and deaths are dependent on the population stock, represented by the control arrows in the diagram. As a result, we have an amplifying feedback loop on the left and a stabilizing feedback loop on the right. What happens with the population overall depends on the relative strength of these feedback loops, an issue we will come back to in a later video. Let's look at an example that involves a more complex flow, resulting in more equilibria to analyze. Phosphorus is an important fertilizer ingredient. As a result, there was an inflow of phosphorus into many lakes. In lakes, plant and algae feed on phosphorus. They also bring more phosphorus into the lake by taking up phosphorus from lake sediment. This creates an additional inflow. In general, the outflow of a pollutant will be proportional to the amount present, as it is carried out with outgoing water. You can read more about this example in the textbook, and we'll return to it in later videos. In the meantime, we'll focus on the graph of the inflow and outflow, plotted against phosphorus levels. Note that the more complex inflow curve. This results in 3 equilibrium points, the 3 points where the inflow is equal to the outflow. To determine if these are stable or unstable, we can look at the inflow and outflow curves nearby. For example, look at the point labeled D, where the phosphorus level is 200 tons. For phosphorus levels just below 200 tons, the inflow is greater than the outflow. This means that the phosphorus level will tend to rise. For phosphorus levels just above 200 tons, the inflow is less than the outflow. This means that the phosphorus levels will tend to sink. In both cases, the phosphorus levels will tend toward the equilibrium, making this a stable equilibrium point.